Now, once we know about the nim sum, we can ask ourselves, how do we win at nim? My claim is all nim positions whose nim sum is 0 are the p positions, and all positions where the nim sum is non-zero, those are the n positions. And as you already should know, if you know all p positions and you know all the n positions, then you know how to win at that game. You know perfect strategy. So first, it's a good question to ask, why is it true that all nim sum 0 position? So what do I mean by a nim sum 0 position? If you look at the number of stones in each pile and take the nim sum of those numbers, if that nim sum of those pile sizes is 0, then we get a p position. If the nim sum's non-zero, we get an n position. Well, we have to check 3 things to check that this claim is correct. We need to know that all terminal positions are p positions. Of course, in nim, there's only one terminal position, and that's when all the stones are taken. That means all piles have size 0, and it's pretty clear that the nim sum, when you have all piles of size 0, is 0. So that condition is satisfied very easily. The trickier ones are the next 2. If we have a position other than the terminal position that has nim sum 0, we want it to be a p position, we have to show that any move from this position will give us something we claim is an n position. In this case, that means we'll have to show it leaves a non-zero nim sum. Well, how can we argue that? Well, if the nim sum is 0, and let me just write down an example of a position with nim sum 0. I'm going to write down the pile sizes in base 2. I don't care what they are, base 10, if just in base 2, if you have, let's say, 5 piles whose sizes are 1, 1, 1, 0, 1, and 0, 1, 1, 1, 0, and 1, 0, 1, 1, 1, and 1, 1, 0, 0, 0, and then let's say 1, 1, 1, 0, 0. I have 5 piles with these sizes in base 2. You can check very easily that the nim sum here is 0, because in every column you have an even number of 1s. What happens if you make any move? If you make any move, you're going to take one of the piles and you're going to take away some stones from this pile. In other words, you're going to reduce this number to a smaller number. Well, what happens when you do that? You're going to have to change at least one of the entries. You can't leave all of the entries the same. And if you change at least one of the entries, one of these zeros will definitely change to 1, maybe more, of course. So taking away any number of stones from any one pile definitely takes a position that had nim sum 0 to a position whose nim sum is now non-zero. And that means that if you started in what we claimed was a p position, every move will lead to what we claim is an n position. Going the other direction here is a little trickier. We need to show that if a position has a nim sum which is non-zero, something we claim is an n position, then there is some move, some special move, which will leave a position with nim sum 0. What move will work? Or what moves work? There might be many different moves, but we need to show that there's at least one. Well, let's look at one example here, and I'll give you the general argument while looking at a single example. Let's say we have piles of 8, 9, and 10. Now, in base 2, 8 is 1, 0, 0, 0. That's no 1s, no 2s, no 4s, just a single 8. 9 is 1, 0, 0, 1, and 10 is 1, 0, 1, 0. And if we look at the nim sum, we'll have a 1 here, a 1 here, a 0 here, and a 1 here, because we have an odd number of 1s in the first, the third, and the fourth columns. So this is definitely a position with nim sum that's non-zero. I want to show you how you can find a move or moves that will turn the nim sum to 0. And I claim the way you do that is the following. You look for the highest position, that means the highest value position, in this case the 8th position, this 4th column from the right, where there's a 1 in the nim sum. Find the entries where you have a 1 in that highest position that contains a 1. Let's look at this one. Let's say I want to take stones from the pile with 8. I'm going to take away that 1 and turn it into a 0, because taking away any stones will change that 1 down to a 0, and that will leave me an even number of 1s in that column. I don't want to alter the next column, but I want to alter each of the next 2 columns. So I want to replace that 1 that I started with a 0, but I want to replace the 0 with the 1 and the 1 with the 1. So I want to replace the 1, 0, 0, 0 with 0, 0, 1, 1. And that's base 2, so that's going to be the number 3. So one move is to the position 3, 9, 10. In other words, take 5 away from the first pile of stones, and you can see that when I replace this, you can write it in yourself with a 0, 0, 1, 1, the nim sum will now be 0. I claim you can always do that by operating on one of the piles that has a 1 in the largest position where any of them have a 1. And that means here you can take stones from any pile to get a winning position. How would you get a winning position if you took stones from the 9 pile? Well, again, we have to turn that first one into a 0 to get an even number of 1s there. We want to leave that 0 alone. We want to change this 0 to a 1, and we want to change that 1 to a 0. So I'd want to replace the pile that had 9, 1, 0, 0, 1, with 0, 0, 1, 0, which is 2. So another move is to 8, 2, 10, take 7 away from the second pile. And you'll see this has nim sum 0 as well. Do check yourself. If you put in 0, 0, 1, 0 here, the nim sum will be 0. And finally, what if instead I just decided I wanted to I wanted to take stones away from the pile with 10 stones. I could do that by replacing the 1, 0, 1, 0 with a 0, and I still want a 0, and I have to change that 1 to a 0, and I have to change that 0 to a 1. I'd want to go down to just a single stone in the pile instead of 10, so I take 9 stones from pile 3 here, and that will leave me with a nim sum 0. The point is, in any position that has nim sum which is non-zero, there will be a 1 somewhere in the highest column, meaning the one furthest to the left, and you can always find a move that turns you into a position with nim sum 0 by replacing one of those piles with a 1 in the furthest left position with something smaller, just by making sure that the smaller thing you replace it with is designed precisely to make the nim sum 0. That's guaranteed to work. So how do you win at nim? If it's your move and the nim sum of the piles is non-zero, an end position, move to a position with nim sum 0, a P position. That means find a pile from which to remove stones. You can always do this by looking for a pile with a 1 in the largest leftmost position of all the piles and taking the appropriate number of stones away, and leave your opponent a P position, one with nim sum 0. Keep repeating the same process until you take the last stone, and then you win. If it's your move and the nim sum of the pile sizes is 0, you cannot win if your opponent plays perfectly. Try to play a small move. Hope your opponent slips up. You still might win. If you're playing family members, you can probably get away with a few mistakes at the beginning. But then be sure to play well at some point when you have an end position and win the game. Here's another Oops, sorry. Let's look at another example or two. Let's say you have 4-pile nim. Let's say you have a 3, a 12, a 14, and a 40. So you have this position in 4-pile nim. Is this a P position or an N position? And if it's an N position, what would be a good move, a winning move? Well, we can look at everything base 2. 3 is just 1, 1. 12 is 1, that's an 8, not a 0. It would be 1, 1, 0, 0, that's 12. 14 is 8 plus 4 plus 2 plus 0, so there's 14. And 40, we need to go to the 16 and the 32 pile. We have a 32, no 16s, an 8, and nothing else. So here are those 4 pile sizes in base 2. We line them up and we ask, what is the nim sum? The nim sum gives us a 1 here, a 0 here, a 0 here, 1, 0, and 1. So the nim sum is definitely not 0. So this is an N position. In order to take away stones from one pile and leave a P position, I have to look for the pile that has a 1 in the leftmost position. Here it has to be from pile 4. If I take things from any of the other piles, you can see the nim sum will be non-zero because that 1 will still give us a non-zero nim sum. So the only possible winning move is to take from pile 4. Well, what do I take? I want to replace this with a number that gives me a 0 in that leftmost position. I want to keep the next 0. I want to change that 1 to a 0 so I get an even number of 1s in that column. So I'm going to have a 0 there. I'm going to want to keep the 0 in the next position. I'm going to keep the 0 in the next position. And then I'm going to need a 1 in that last position. So what does that mean? Well, this number is a base 2 number, and that's clearly just the number 1 in base 10. So I take 39 stones from pile 4, and that leaves me, replace this number with a single 1, and you'll see that you'll get a nim sum 0. That's the only winning move in this position. And let me tell you, if you're playing your friends and they haven't studied this, there's no way that they'll guess that one move is the only winning move. So if you give this position to your friends, let them go first. If they make any mistake, they don't take 39 stones from pile 4, you can then find the new winning move and then continue to find the winning moves and always leave them in P positions after that.